Now we'll see the language accepted by Turing machine. Okay, they are known as recursively enumerable languages. We have to discuss recursively enumerable languages and recursive language. So what is recursively enumerable language and what is recursive language, we will see. So this recursion is different from your recursion in your algorithms and C programming or any programming. Okay, these two are quite different. Otherwise there is no relation, forget about that. Now what is the recursively enumerable language? Very simple. So let's say this is your Turing machine. Okay, now Turing machine accepts a language, correct? Whenever a Turing machine accepts a language, then that language is called recursively enumerable language. That means recursively enumerable language is nothing but class of languages L1, L2, L3 for which there is a Turing machine. That means Mr. L1, do you have any Turing machine for your language? Yes, example WW. Now Mr. L2, what kind of language you are? I am WW reverse. Mr. L3, you are what kind of language? Something else. In that way, all these languages are, let's say, accepted by some Turing machine. Then we say that these languages are recursively enumerable languages. Like, regular languages. All the languages accepted by finite automata is regular, right? In the same way, all the languages which are accepted by Turing machine is recursively enumerable language. Example, you have a language. Whenever it claims that I am recursively enumerable, then definitely we can imagine that there is a Turing machine for that. Example, let's say there is no Turing machine for some language, then that cannot be recursively enumerable. That is the definition of recursively enumerable language. Remember it. Now, sir, what is recursive language? To understand recursive language, you should understand a machine called total Turing machine. Let me define total Turing machine. So what is total Turing machine? If you want to understand, first of all, let's begin with just ordinary Turing machine. Okay. Now generally any Turing machine's behavior, if you see, it will be like this. You give an input and because of that input it will run. Then eventually that Turing machine is going to accept state, correct? That means T state. So let's call it as accept state. Whenever it goes to accept state, we say that input is accepted by this Turing machine. Okay. Now if this W1, sometimes what happens, it will go to reject state R. Then we say that input is permanently rejected. Now sometimes what happens, your Turing machine will run forever and it neither goes to accept state nor goes to reject state. Then we say that it is looping. Okay. So there is a loop. That is one tricky part, otherwise one disturbing part, I can say. Because of that, your Turing machine becomes so complex. Now here, remember one thing, any Turing machine will have generally this behavior. It sometimes accepts, sometimes rejects, sometimes loop. But we don't know when it loops, that's a problem. Okay. Now whenever you have a language, example, let's say this Turing machine is Turing machine for language L. Okay. So L is the language for which this is a Turing machine. Then W, let's say one of the input belongs to L. That means what? We have designed a Turing machine for a language and your input is one of the input from that language. Then definitely what it is going to do? Your Turing machine is going to accept it 100%. Definitely it won't loop. If it loops also, not loops forever. It is not infinite loop. Okay. So surely it will come out of the loop and it will accept it. Now if you give an input which is not part of that language, or W does not belongs to a language, then if you give such kind of input, then your Turing machine may reject it, otherwise sometimes it may loop it. That is one serious thing you have to concern. Okay, remember it. Finally, let me summarize about general Turing machine behavior. You have designed a Turing machine for a language L, and let's say your W, which you are giving currently as input, belongs to your language. Definitely it will go to accept state. Why, sir? If it won't go to accept state, then how it will be a language for that Turing machine? I mean, how it will be Turing machine for that language? Correct. Really, it is a Turing machine for a particular language. All the strings in that language should be accepted by Turing machine. Okay. Example, you have a washing machine, and then I asked you about that washing machine. If I put a t-shirt, will it wash? Let's say if it won't wash, it says no, I don't wash, then that is not a washing machine. Correct. That's why whenever really it's a correct washing machine, every cloth it should wash, and if you put any stone kind of thing, then your washing machine is not designed for this kind of input, okay, then it can do anything. Maybe it can say no, I don't wash. Second one, it may try to wash it like this. So that is a danger with washing machines, correct? So they don't reject anything. Similarly here also, your Turing machine, if you give a valid input, then they may accept. If you give invalid input which is not part of your language, so they may reject, otherwise may loop. So there is no differentiation between these two. Anything can happen, remember it. Now we will see total Turing machine. Total Turing machine is nothing but a Turing machine which will have only two functionalities. Eventually, definitely it will accept sometimes, it will reject sometimes, remember it. There is no looping. So that is one great thing about total Turing machine, okay. But we don't know which one is total Turing machine, which one is ordinary Turing machine. That is a problem. But this is a fundamental definition of total Turing machine. If someone says that they have Turing machine which is total, definitely you can understand that if input is given, and let's take the language first. Let's say this total Turing machine is total Turing machine for a language L. Now if you give a string W which belongs to that language, then definitely this total Turing machine is going to accept it eventually. I don't know time, but definitely after finite amount of time it accepts it, because that is the way that Turing machine is designed. Now if that W does not belongs to L, then it won't loop forever. It will definitely eventually come out of the loop and it will reject it, but it won't accept. That is the definition of Turing machine, correct? So the difference between these two is both are accepting the right inputs, but here this Turing machine may reject, otherwise go into loop. But for wrong inputs, this Turing machine definitely rejects it, okay. Like in our real life also we write programs, okay. So our focus was generally, while writing the programs, our focus will be on logic, right? We try to write a program. Generally, for example, you write a factorial function, then our entire effort will be, we put so that whenever a right input is given, it will correctly work. Such a way we write it and we will be very happy. But in that process, what can happen is sometimes people give negative numbers like -23. What happens? No one knows, because you did not think about that while writing the code, correct? At that time, what happens? You tell me, try to write a factorial program, don't think about wrong inputs, then you try to write it. Then what happens if someone gives unexpected input like -23 or something? Then we don't know what happens to your program. It can give anything, because you did not write any code for that. So anything can happen. It may go to infinite loop. Sometimes you might have observed, right? So that is the way your Turing machine is also going to do, okay. So now we have two kinds of languages: recursively enumerable language, recursive language. Let me summarize. If any Turing machine, if you have a language and if that is accepted by some Turing machine and it is ordinary, let's say, I don't know whether it is total or not, I don't know, then we say that language is recursively enumerable. Now you have a language, for that definitely I have seen some total Turing machine, then we say that that is recursive. And remember one thing, total Turing machine also a Turing machine, correct? So that's why, so total Turing machines are proper subset of these Turing machines. Remember one thing, okay? So that's why recursive languages are subset of recursively enumerable languages. Let me clearly tell you one more time, okay? Before that I erase it. Now we'll see some of the differences between total Turing machine and Turing machine, and the story related to them. Well, let's begin with total Turing machine. What do you think total Turing machine is? It is very simple. It's a Turing machine first of all. Why? Because it is going to have infinite tape, semi-infinite tape, and it is going to have same everything, like so inputs alphabet, tape alphabet, everything, and it is going to follow the same rules like a Turing machine. But the code is such a way that means the person who wrote that code is such a way that the behavior was like this. Whenever a right input is given, that means, example, let's say you have designed a total Turing machine for some language, okay, like WL equal to WW. But the person who designed the code, he designed such a way that whenever you give a right input, okay, then he is accepting it. That is the essential thing. That means any Turing machine, if it is really a Turing machine for a given language, if the input is given from that input given language, definitely it should accept it. Otherwise, it's not a Turing machine for that language. Fine. But if you give another input, like example A B B A, this is not in WW format, right? Then such Turing machine, first of all, any Turing machine should not accept it. But it is not compulsory that we have to reject it. Maybe you can go to loop also. That is what Turing machine's behavior, already I told you. A general Turing machine, that's why behaves like this. If right input is given, what is right input? An input which belongs to the language for which you are constructing the Turing machine. If it is given, then it definitely accepts. And if you give wrong input, then it may do two things. Maybe it will go to loop, otherwise it will reject. Okay, so two things. Now this is exactly like server behavior. This is an analogy. So there is a hotel. In that hotel there is a server. Okay, that server is, let's say, Raju, and Raju is going to have this behavior exactly like general ordinary Turing machine, how it is. See, example, if you go to that hotel and if you ask Raju, my dear Raju, what do you have in your hotel? Then he will not tell, because he is not designed for that. Your Turing machine is designed for what? When you ask a question, it will answer, right? So you have to ask a question like, my dear Raju, do you have idli in your hotel? Then they will have something in their menu like idli, okay, so dosa, something, okay, and poha, everything. Now he will see that list. Really, now it is his language. Now if you ask a question or input, if that input belongs to their language, then Raju says yes. Then they will do anything for you. If you ask idli, they say yes, we have sir, and they serve. If you ask dosa, definitely they serve because they have it in their menu. If you ask, do you have something like noodles? If you ask, now this is the input. You are checking whether that belongs to your language or not, but that in Raju's language it is not there. Then what Raju can do is, he can do two things. He will reject it. That means he say, no sir, we don't have noodles, we don't accept noodles. Second thing what he can do is, he will go to sometimes infinite loop. Why? Because if he rejects, I'm just giving analogy and don't try to exactly follow that for Turing machines also. So example, why sometimes Raju rejects, I will tell you. If he rejects it, if he says sir, we don't have noodles, you will go to another hotel where that is served, correct? That's why he want to keep you in infinite loop, so that Raju never tells answer. Then you will be waiting for his reply. So after some time you will get frustration and angriness and hungriness. Then what you do? You change your order. Then you ask Raju, leave it. I don't want to eat noodles now. I changed my mood. Do you have poha? Then he will say immediately yes, because he accepts it. So that is a Raju's behavior. Now you ask again, do you have biryani? Then Raju says two things. Maybe he says no, otherwise to keep you in a loop so that you can order something else. So he will say, sir, wait sir, I will tell you. I will go inside and I will consult my management and I ask whether we have biryani or not. But he never comes back. Then you will be waiting here for him. He will not come, like a Turing machine. So Turing machine is also exactly same. It will keep you busy if you give wrong input. Example, let's say this Turing machine is designed for a language L. Remember it, okay? This is a Turing machine for that. If you give input W which belongs to L, that's why definitely he will accept. Like asking, idli, dosa or poha, because that belongs to language, they will accept. If you give an input which is invalid input and your Turing machine is not designed for that, then he will reject, otherwise he will go into loop. Okay, so either loop or reject or loop. So that is about ordinary Turing machine. Now we'll see one more behavior. So there is second kind of server possible. Let's say Rani. So she is little bit straightforward and honest, and she is innocent. Now she has, let's say she is working for some hotel now. Now she will have list of elements like idli, so dosa. I can say these are all strings of her language. Let's say this is language, so that we can connect it to our language problem. So Rani is having a language and Rani is a Turing machine for this language. Now if you ask a question, Rani, do you accept idli? Then she will say yes, because idli belongs to her language. Now if you ask Rani, do you have dosa? She will say yes. Now if Rani is total Turing machine, let's say, then what she is going to do is, now if you ask Rani, do you have idli? She say yes. Dosa, eventually she says yes. Rani, you have biryani? If you ask that question, since biryani does not belong to her language, then simply she says, no sir, we don't have, we don't serve. Directly you go to another hotel, so don't waste your time. So that is the total Turing machine's behavior. Okay. Now total Turing machine also exactly like a Turing machine, but because of your sophisticated code, we have designed it such a way that either always we are going to, for on any input, we are going to T state or reject state. That means we are going to final state, otherwise reject state. Such a code if you write, then we say that yes, we have a Turing machine which is well behaved Turing machine, and that is total Turing machine. That's why total Turing machine is also a Turing machine, but it is well behaved Turing machine. That's it. Now we will see more details about this Turing machine and total Turing machine. Question number 1. Sir, I have a language, for that I have a Turing machine. I have designed it, but I don't know whether it is total Turing machine or not. Okay, fine. But my question, can we always have total Turing machine for any language when we have ordinary Turing machine? I guarantee that there is a Turing machine, sir. I have designed it, but I don't know whether it is total Turing machine or not. Now my question is, can we guarantee that there is a total Turing machine? May not be this one, but some others can design it. Such a Turing machine exists. So that is a question. Let me summarize it again. What I am asking is, there is a language, for that already there is a Turing machine. Now I am asking, for such language, can we guarantee always total Turing machine? That means for whatever the language there is a Turing machine, can we convert that Turing machine to total Turing machine? Is a definitely very interesting question, and that is about decidability kind of thing. We will see that. So here definitely for every Turing machine, total Turing machine is impossible. There are some languages for which there are Turing machines but not total Turing machines. I am going to prove that. Remember it. Okay. So from now onwards, it is not compulsory that if your language has a Turing machine, then there is a total Turing machine. Second thing, let me ask one easy question. This time you have to answer it with your common sense. There is a language, for that there is no Turing machine. Okay. Now let's say you can take the help of God, but you have to construct a total Turing machine. Is it possible? You don't have Turing machine for that, for sure, but can you construct total Turing machine? Said that's why it's very easy question. Impossible. Why? If you can construct total Turing machine is a Turing machine, but already we know that there is no Turing machine. How can you have Turing machine? Correct, sir. God is giving us Turing machine, sir. God can do anything. Let's say really God can do anything, then God gives you Turing machine, which is total Turing machine. Total Turing machine also Turing machine. Then this one is wrong, right? Saying that we don't have Turing machine is wrong. That's why whenever a language doesn't have Turing machine, definitely it cannot have total Turing machine, because total Turing machine is also a Turing machine. It's a simple question, of course. Okay. Now these are all some details about your recursively enumerable language and recursive languages and Turing machines and total Turing machines. Let me summarize it. A language, from now onwards, this statement is very important. Please stick to this. Don't use your definitions. Blindly remember this one. You have a language and you want to say whether it is recursively enumerable or not. You want to check. Simply construct a Turing machine. If you can construct it, that is recursively enumerable. Sir, I don't have so much logic, sir. That's why I couldn't construct. Then it means it is not Turing machine. It is not recursively enumerable. It's not like that. So you are asking this question. There are two people, you and your friend. There is a language and you want to prove that it is recursively enumerable. For that you tried Turing machine, but you didn't get it. But your friend got it, Turing machine for this one. Then Sir, can we say like that? For my friend it is recursively enumerable, for me it is not recursively enumerable. Then I ask why? Because I didn't get any Turing machine. Maybe you are lazy, that's why you didn't get it. It doesn't mean that everyone is lazy, correct? That's why definition is not like that. Now I would like to change the definition. So here definition is not about you. If no one can construct a Turing machine, if you can prove it, then that language is not recursively enumerable. But if at least someone can construct it, that is definitely recursively enumerable language. Remember it. That is the definition of recursively enumerable language. If someone can construct a Turing machine for any language, that is recursively enumerable. Second one, similarly, if someone can construct a total Turing machine for any language, such language is called recursive language. That is a definition of recursive language. Remember it. Now, you can't do this kind of thing. There is a problem and you tried it, okay, and you tried constructing Turing machine, but you failed it after some time. Then don't say anything, because you don't know anything about that, because it is your problem. You did not prove that there is no such construction, correct? Really you want to say that there is a language is not recursively enumerable. For that you have to prove that no one can construct it. Like, you should not construct. At the same time, you should give a mathematical proof that, sir, in the world no one can construct such machine, which is very difficult part. Okay, generally it is very difficult to do that, but we can do it. I'm going to take some examples and I'm going to prove that there are some languages. I show you and I prove that they don't have Turing machines. They cannot have Turing machines in the future also. Even God cannot construct a Turing machine for it. Okay, because we are going to give a mathematical proof for that. Then you have to agree on that. Okay, we'll see that. Now we'll see some important results about your recursive languages and recursively enumerable languages. First of all, let me start with simple point. That is, if L is recursive, then automatically that is recursively enumerable. Of course, that is obviously true. So recursive, then L is recursively enumerable. Okay, you know the definition of recursive language. Really L is recursive. Definitely there is a Turing machine, especially total Turing machine. Okay, remember it. Now that means automatically that is recursively enumerable. Why? What is the definition of recursively enumerable language? For that there should be a Turing machine. Whenever you have a total Turing machine, that is also a kind of Turing machine. So automatically we can say that L has a Turing machine. So when L has a Turing machine, that will come under recursively enumerable language, right? That's why from now onwards, whenever a language is recursive, then it is automatically recursively enumerable. But reverse is not true. That means may not be true. You have a language, a random language that is recursively enumerable. Then can we say that always L is recursive? We don't know. I'm going to prove at this moment. You remember, whenever L is recursively enumerable, it is not compulsory that L is recursive. There are some languages which are recursively enumerable but not recursive. Okay, we will see that. But here, what is the reason for that? If you want to know, I'm going to show one language, okay, after some point of time. So that is recursively enumerable, okay, but not recursive. That's why we can always remember this picture. These are all group of recursive languages which have total Turing machines. Now there are some special languages for that there are Turing machines but not total Turing machines. At least there is one such language. I am going to show that. That's why now at this moment you remember, definitely there are some languages which are recursively enumerable but not recursive. So that's why this will be the diagram. Recursive languages are proper subset of recursively enumerable languages. Now let me ask some questions. A language is recursive, then automatically that will come under bigger circle. So recursively enumerable. If a language is recursively enumerable, then that may be here or here. So if it is here, definitely I can't say that that is not recursive, correct? That's why there are some languages which are recursively enumerable but not recursive. That's why I can't always say that whenever a language is recursively enumerable, it is recursive. We can't guarantee. Now we'll see little bit difficult statements and we try to prove them. The important result is whenever a language is recursive, then its complement is recursive. You know complement language, right? So automatically we can construct recursive language for L bar. Okay, why we will see. First of all, let's begin with L. What is given? L is already recursive. If L is recursive, what do you know about L? it has a Turing machine, especially total Turing machine. This is a starting point. That means someone already written a code such a way that if you give input, now see, for your language, whenever there is a Turing machine, so with respect to this diagram, so you can understand like this, there will be accept state and always reject state. That means whenever an input is given, question number 1, if really that input belongs to the language for which you have written a total Turing machine, then it will accept it. If W does not belongs to L, then the input which is given is not part of the language, so it will definitely, total Turing machine is going to reject state. Okay, sir, is it always possible? Yes, that's why we say it is total Turing machine. Sir, total Turing machine never loop? Yes, it won't never loop. If it loops, then that is not total Turing machine. Remember it. Okay. Now in that way, when you have a recursive language, definitely there exists a total Turing machine. I am not saying that whatever the way you construct that automatically will become total Turing machine. It is wrong argument. So example, let's say Raju is thinking like this. There is a language WW. Now he is designing a code for that. That means he is writing a code like this. Q on A is something something something. Q on B and something something something. So he said, sir, this is my Turing machine. Now is it total Turing machine? I don't know how you written. Correct? Maybe you have written ordinary Turing machine. So that if you know WW format, it is detecting correctly and it is going to accept state. That means if your input is in WW format, it is accepting. But if it is not in WW format, then your total Turing machine may be going into loop. Who knows? So how you design, we don't know. But still we say that this is a Turing machine. Okay. But we cannot guarantee that you have a total Turing machine. So that's why what I want to say is, whenever a language is recursive, then there is a total Turing machine. That means someone can definitely construct such a way that for right inputs, it accepts. For wrong inputs, it rejects. But it doesn't mean that whatever the way you construct a Turing machine, that automatically becomes total Turing machine is absolutely wrong. Still, I can construct a Turing machine which loops sometimes. Right? Remember it. Now, when you have a total Turing machine, assume that let's say we have already constructed total Turing machine because we can. Right? And whether we construct it or not doesn't matter. They exist. Correct? Understand? So we are not constructing, we are assuming that there is a total Turing machine. That is a fundamental definition of recursive language. Now we are going to prove that L bar is recursive. That means we are going to show total Turing machine for L bar also. For that, what you do is you read the code. Okay, definitely in that code there is a accept state, there is a reject state, correct? Now what you do is you change the code such a way that whenever your Turing machine here goes to accept state, make it reject state. Whenever you have a reject state, all the activities, example, you have you have this kind of thing. Q on A is going to T, like this. You have code like this. Simply modify it and make it R. And you have a code like Q on A, let's say it is going to reject state. Modify it and make final state. In that way, make all final states to reject states, reject state to reject state to final state. If you do that, what happens? Indirectly, pictorially I show that. Finally, what are you doing is, whenever you have an accept state, you are making it reject state. Such a way we are modifying the code. Yes, we can do it. When you have a reject state in that one, all that reject state we are making into T state or final state, so that it will accept. Try to understand. Simple. Wherever you have T, make it R. Wherever you have R, you make it T in the code. When you do that, what happens? This behavior will happen. What is that behavior? We will see. Because of that, the same Turing machine, so-called total Turing machine, it was like that. Initially, happily it was having accept and reject behaviors. But you modified the code, that's why, because of that, what happens is, this is now your new code. How your new code is behaving, you see. When it was accepting, because of your modification, now it is rejecting, because you made T to R, R to T. Then the rejected inputs will be accepted. Agree? Yes. Now you see, I created a new machine. Try to understand that new machine, how it looks, how it behaves. give input to W. Then that input will be taken by this total Turing machine. Since you modified, final to non-final, non-final to final. Did you remember? So you made T to R, R to T here. So because of that, your behavior will be exactly accepting all will become rejecting, rejecting all will become accepting. Remember it. So now let me summarize what is going to happen. Whatever the input you give to this modified machine, so if really, let's say this is Turing machine for L, correct? Initial Turing machine. Really your language, your input W belongs to L. Then what this machine is going to do? This new machine is going to reject it. Remember it. Then reject it. Now if W does not belongs to L, then your original Turing machine was rejecting, because that is total Turing machine, definitely it rejects. Then reject state you made final state, then it is going to accept. So then accept. Now if you look closely, whenever an input does not belongs to L, we also say that belongs to dash L bar. If W belongs to L, then we also say W does not belongs to L bar. So what is happening, you see, W belongs to L bar, then your machine is accepting. W does not belongs to L bar, your machine is rejecting. Then finally you formed a total Turing machine for dash L bar, correct? So that's why it is total Turing machine for total one, you see. That's why whenever the input is given here, if it belongs to L bar, it is accepting. If it does not belongs to L bar, it is rejecting. So exactly it is total Turing machine for L bar. So finally we have a total Turing machine for L bar, then automatically that is recursive. That is a fundamental definition of recursive language, right? Now we'll see second one. If L and L bar is recursively enumerable, then automatically it is recursive. Why, we will see. There is a language L, so that L is recursively enumerable. L bar is also recursively enumerable. If that is the case, automatically that language will become recursive. Why? We will see. Now we'll see why L is recursive. Simple. To prove that L is recursive, finally we have to prove this one. We have to show that there is a total Turing machine for what? L. That means we have to design a total Turing machine for L such a way that if input is given, either it should accept if really W belongs to L, otherwise it should reject. Such a machine is possible or not, we will see. First of all, let's observe one thing. L is recursively enumerable. For that we have a total Turing machine, recall. So let's call it as Turing machine 1. It is a Turing machine for what? Language L. So what is it going to do? We will see. Since it is a Turing machine for L, then if you give input W and it is a ordinary Turing machine, so if the input W belongs to, I am just observing the behavior of Turing machine 1. W belongs to L, it is going to be accepted. Let's write A. Now if the Turing machine, if the input does not belongs to L, then it is going to either loop, otherwise reject. That is a problem. Now we have another Turing machine. What is that? Turing machine 2. For what? L bar. See, L bar is also recursively enumerable. For this Turing machine 2, if you give input W, then let's say this is Turing machine for L bar, right? Then if that input is accepted by this Turing machine 2, means what? It belongs to L bar. Remember it. If W belongs to L bar, then it says yes, accept. Otherwise it will reject. Otherwise it will go to loop. Correct? So this is the behavior of Turing machine 1. This is the behavior of Turing machine 2. Now using these two, we are going to construct a new Turing machine. How it looks like, you see. So here, using the Turing machines is nothing but using the code of Turing machine 1, using the code of Turing machine 2. In C programming, example, let's say you have two modules or two functions. Then using that functions, we can write a bigger problem, correct? We can write a bigger program. In the same way, using the code of Turing machine 1, using the code of Turing machine 2, by combining them, I can write a bigger code. Let's call it as Turing machine 3. What this Turing machine 3 is going to do, I will tell you. This Turing machine 3 is going to be total Turing machine, remember it. Such a way I am planning, so that, and for which language L. This is the total Turing machine for language L. If I really can construct it so that if input is given, either it should accept or reject. We know when it accepts, when it rejects, right? Such a Turing machine, if I can design total Turing machine, then you should accept that L is recursive. Why it is possible, I will tell you. I take the code of Turing machine 1 here, and I take the Turing machine 2's code also. Turing machine 1 contains accept state, reject state, correct, and sometimes it will loop. Similarly, Turing machine 2 is also going to accept state and reject state and loop. Now remember one thing, this accept is not our final accept. I am not saying that. Similarly, this reject state of Turing machine 1 is not our final reject. Okay, we have a separate reject state. So here this is final accept, final reject. Now the Turing machine 2 is having accept state separately, reject state separately, and looping separately. Okay. Now what I do is, whenever input is given to my Turing machine 3, I did not tell you the functionality of this overall machine, right? I'm going to tell you. First, that input will be run using this code. Okay, for one step. Then I also run this Turing machine 2's code also in the next step. In that way, I run one step of Turing machine 1 code and one step of Turing machine 2 code. In that way, parallelly I run both of them. Then eventually, what happens? So your W may be accepted by this Turing machine 1. Then I connect this acceptance to acceptance, you see, A to A. I connect this acceptance to reject state of final. Okay. Now just observe when a string is accepted, when it is rejected first of all. Okay. Now see here. Assume that first of all W belongs to your language L, because it is really a Turing machine for this language L. It should do what? Really it is a total Turing machine for language L. Really W belongs to L. If W belongs to L, then the Turing machine should do what? Accept. We will see why it will do that. Since you are running both Turing machines simultaneously, so W will be eventually accepted by Turing machine 1. Why? It is a Turing machine for language L. If it accepts, you are accepting, then definitely you are also accepting whenever W belongs to L. Note down. So whenever W belongs to L, then your Turing machine 3 accepts it. I am writing the information. Next. Sir, what if W does not belongs to L? Then it is going to loop, otherwise reject, sir. Yes, it is going to reject, otherwise it is going to loop. That is a trick. If you don't use Turing machine 2, then we can't construct total Turing machine. Why? If it loops, then I also have to loop. I can't reject because I don't know really that is a loop or it is pretending like a loop. Correct? Then if you think that it is loop, then it might turn out that it is not a loop. I will give you one analogy here. Example, let's say there is a Raju and hotel, and you are asking him idli, and let's say don't see this one, it is just for our reference. Now we ask Mr. Raju, I want idli. Recall Raju's behavior. He is a Turing machine. If really he has idli in his hotel, then he will bring it eventually, maybe in 1 hour, 2 hours. But if you ask biryani, which is not in his hotel, but you don't know whether it is there in hotel or not. If you know that it is not there in the hotel, you would have gone to another hotel, correct? That's why we don't know, we are not sure. That's why we are asking Raju, my dear Raju, do you have biryani in your hotel? Then what he says? If really it is there in his hotel, eventually he will bring it up. If it is not there, then there are two options. Raju after some time might come and say, sir, we don't have that. Second thing, he will say, sir, please wait in this room, we'll come and serve if we have. I have to consult my manager. I will consult and I will come back, and he will never come back. That is also one more possibility. Now, what you are doing is, you are planning like this. You want to wait for 1 hour. After 1 hour, let's say you want to leave, and you are assuming that let's say biryani is not there in the hotel. But what can happen whenever you leave after 1 hour, by assuming that let's say Raju went to infinite loop, you are guessing that there is an infinite loop. Whenever you go out, he will come back and he says, sir, why are you going out? We have biryani. That means whenever you are guessing that it is a loop, that might not be loop. That's why always we can say that we don't have clarity whether it is really a loop or not. That is a danger. Really you know that something is going to be a loop, then definitely we can decide something. Example, let's say when it loops, we reject, but we don't know that that is loop. Here also same thing. You tell me here, when we have to decide that biryani is not there in the hotel, Really it is there in the hotel, he will serve. If it is not there in the hotel, he will make you wait, otherwise he will he will say that there is no biryani. Now 100% I can say that you can't decide after some finite amount of time. Definitely takes infinite time for you to decide. Why? After 1 hour if you go suddenly, then he will bring it. If you wait 2 hours, after that if you leave, then at that moment he can bring it. Then let's say you waited for 1 hour, 1 year. After that, let's say because of starvation you did, then after that he can come and he says, I'm sorry, we are late, but we are serving hot, please take it. That means we can't say really biryani belongs to their language or not. In the same way, using the Turing machine, we can't say whether some string is rejected or not. But if it is accepted, definitely that machine is going to say, I accept. If W does not belong to this language, so there is a danger that it will go to loop, then we can't decide. Then we also have to loop. We have to wait. But don't worry, this is not the case here. Why? We have our friend Turing machine too. Who is this Turing machine? He is Turing machine for L bar. Okay. Now, really W, let's assume that let's say your Turing machine 1 is in the loop. That means what? W does not belongs to. I am assuming the case that W does not belongs to L. That is what your problem, right? Really W belongs to L? We are accepting it. That is what we have to do and we are doing. If W does not belongs to L, but since we are running Turing machine 2 also simultaneously, eventually W does not belongs to L means W belongs to L bar. Both are same. If this is Turing machine 2 for L bar, then definitely he will accept it. Okay. So he will accept it. Whenever he is accepting, you are rejecting. Yes, I have to reject. Why? Because this is a Turing machine for a language L. Now you see, whenever W does not belongs to L, W belongs to L bar, both are same, then this Turing machine is accepting, then I am rejecting. When I reject it, I am right because your W does not belongs to L. Finally, W belongs to L, he will be definitely saying yes, I say yes. If W does not belongs to L, definitely he is going to accept it, then in that case also I can reject because I should reject. Then finally I have a total Turing machine. No one can deny. No one can prove that I am looping at any time. Why I never loop? Because either this or this will help me to terminate the loop, correct? That's why, so we have always total Turing machine for L. Whenever L and L bar are having Turing machine, that's why this statement occurs. What is that? Whenever L and L bar are recursively enumerable, automatically L will have total Turing machine, so L will become recursive language. You have to remember this statement very clearly, because most of the times they ask questions related to this kind of fundamental definitions. Okay.